Hello, and thank you for studying CCNA with Vombar. With this lecture, we'll extend our knowledge of the layer 2 topologies, or in other words, topologies where switches operate, and we'll do this by introducing a concept called spanning tree protocol, or just STP. And we'll use STP to optimize our networks. But first, before we go into STP, we would have to talk about some of the problems of redundant topologies, and what actually a redundant topology is, and then we'll see how actually spanning tree works and how actually spanning tree creates those loop-free topologies. And then we will talk about some different types of spanning tree protocols like per VLAN spanning tree protocol or rapid per VLAN spanning tree protocol. And then we will learn how to configure rapid per VLAN spanning tree protocol. A redundant topology is basically a topology that eliminates a single point of failure. So if one of the links of communication actually fail for some reason, I will always have a backup link of communication, and in this way I will not disrupt my normal communication process during work hours or in your company. Well, the problem with this whole thing is that the redundant topology, as good it is and as necessary it is, introduces some problems in the layer 2 topologies. Some of those problems are broadcast storms, smooth per frame copies, or what we know as scam table instabilities, or in other words, MAC address tables instabilities. But first, let's see what the broadcast storm actually means. Well, now imagine host A is to send a broadcast to everyone. Well, when the switch A receives that broadcast, by the nature of itself as a switch, the switch A has to send the broadcast throughout all the ports except the originating one. That means that he needs to send the port through F01 and F02. But let's see what happens when we just send it through F01. Well, when they send the broadcast through F01, and when the broadcast is received by switch B has to do exactly the same thing as switch A did, meaning he has to send it throughout all the ports except the originating one. Well, he received the packet through F01, that means he has to send it through F02. And of course, the link through switch X, but we're going to talk about this in a minute. And then this broadcast, when it was sent by switch B, it was received by switch A, and switch A will have to do exactly the same thing, meaning sending the broadcast throughout all the ports except the originating one. And in this way, the broadcast packet calls up some sort of a broadcast spiral that can actually disrupt your network. And needless to remind you, in the beginning, when we receive the broadcast, switch A has to send another broadcast, but through F02, which will do exactly the same thing as the previous broadcast packet that we just observed. And in this way, both of the broadcasts will create some sort of a double spiral that can actually potentially bring down your network and all your communications. Another problem associated with redundant topologies is what we know as multiple frame copies. Well, if we go back to the case of the broadcast, when the switch A sent the broadcast to switch B had to send it to all the ports except the originating one, if you remember. Well, that causes to send it through F02, but it also caused it to send it through F03. So the switch received a copy of that broadcast. But when switch A received a copy of that broadcast as well, he has to do exactly what every switch does, meaning send it throughout all the ports except the originating one. So eventually, this broadcast goes back to switch B, and with every turn, with every loop, switch B has to send another copy of that frame to server X. Well, computers are not smart devices, meaning that they are not designed to operate efficiently in case of some anomaly happens. And receiving the same exact frame multiple times for the computer is actually a big anomaly, and sometimes they might even crash or they might do unexpected things. And last but not least, another problem associated with redundant topology is what we know as scam table instabilities, or as I said, which is the MAC address table instabilities. Now imagine that host A is connected to switch A on F03, and the host A's MAC address is this MAC address. When originally host A sent the broadcast, the switch A, before sending it throughout all the ports except the originating one, as we already know, the switch A will read the source MAC address of this frame, and he'll populate his table. He uses this approach, as we saw before, so it can perform an intelligent packet forwarding, meaning sending the packet only to the correct port to reach the destination. So when it read the source MAC address, which was the source of host A, he'll put the MAC address of host A in his MAC address table, and he'll put the port from which the frame came, in our case F03. And then this was because this is a broadcast, the switch A has to send it, and when the switch B receives that broadcast, he'll do exactly the same thing as switch A, meaning he'll put the MAC address of host A associating with F01 because that's from the port where the packet came, and the source MAC address was the MAC address of host A. Now when this broadcast, because it's a broadcast, is sent throughout all the ports except the originating one by switch B, now switch A received that same frame with that same source MAC address through F02. Now he thinks that somebody unplugged out host A and plugged it back to F02, or from the place where he actually received the last packet with that MAC address. So now he's forced to change the MAC address table and put in the new port, or the latest port from which switch A received the packet with that same MAC address. Well, now the MAC address table of switch A will look something like this. And the switch A thinks that if he has a packet with a destination MAC address of this MAC address, he has to send the packet through F02. Now, and that what actually happens if server X is to send some packets to host A. When the packet is received by switch B will take a look at the MAC address table, and he'll see that in order to reach this MAC address, or eventually host A, he needs to send the packets through F01. Well, but when the packets are received by switch A from port F01, when he takes a look at his MAC address table to determine throughout which port to send the frame, he looks at F02, and that's where he's going to send the packet, and which inevitably will send back the packet through switch B, causing a loop, or in the end, causing the packet to never reach its destination, which was host A. Well, the solution to all the redundant topologies problem is something what we call spanning tree protocol, or just STP. The way that spanning tree protocol operates is by blocking one of the redundant paths, or probably all the redundant paths, and leaving only one way of communication between the devices. So when devices communicate, and if for some reason this link of communication fails for some unknown reason, what a spanning tree protocol will do is it will actually unblock or open the blocked port of communication between those devices, which allowing those devices to actually operate with normal manner and no interruption of the service. But now let's see exactly how spanning tree manages to block and unblock ports, and so forth and so forth. Well, it is said that spanning tree maintains and creates a loop-free topology is by exchanging small packets called BPDUs, or bridge protocol data units. But we'll focus on those small packets in just a few minutes, and let's see how exactly spanning tree protocol creates a loop-free topology. The way the spanning tree protocol creates the loop-free topology is by selecting a single switch among all the switches in the topology to act like a reference point. We'll call this switch from now on a root bridge, and it is said that the root bridge is selected, is the switch with the lowest bridge priority. Now every switch has a bridge priority, and the default priority is 32,768. You can of course change the value, altering the configuration, altering the root bridge election, and thus altering your entire loop-free topology. But as we said, the root bridge from now is the switch with the lowest bridge priority. In case if the priority is tied, just like in our case here with switch A and switch B, then the root bridge is said to be the switch with the lowest bridge MAC address, or the lowest MAC address. Well, in our case, the MAC address of switch A is lower than the MAC address of switch B. That is why switch A is said to be the root bridge. Well, another thing is that it is said that all the ports on the root bridge are designated forwarding, or meaning that they are open to send and receive traffic. So it is just like the old saying where it says that all roads lead to Rome. And just in this case, all the ports on the root bridge are also open to send and receive traffic, so that every other non-root bridge will be able to establish a loop-free topology that is pointing to the root bridge. In other words, you can actually think of the root bridge to be like your reference point of the entire topology or every other root bridge. Just like the equator or the Greenwich meridian, we use those for referencing, and in our geography we can use here the root bridge as a reference point on all other switches, so they can actually establish a loop-free topology. Well, after we selected the root bridge, every non-root bridge is set to select a single path to the root bridge and then block every other path. Well, the path to the root bridge is selected by what we know as cost, and the lowest cost wins. The cost is basically a value associated with the bandwidth of the interface, and starting like this. For 10 gigabit bandwidth of an interface, we have a cost specified by 1. On 1 gigabit, we have cost 2, and for 100 megabytes, the cost is 19, and for 10 megabytes, the cost is 100. So every non-root bridge chooses the path with the lowest cost that takes into the root bridge, and the port that is connected to that path, or the port on that path, will be called a root bridge. In our case, switch B has two possible paths, or two possible ways to go to the root bridge. One is through F01, one is through F02. On F01, he has a bandwidth of 1 gig, that is why his cost is going to be 2, and another link through F02 that has a bandwidth of 100 megs, which means that the cost is 19. Obviously, the F01 port wins because it has a lower cost, and this port, as we said before, is what we know as a root port, or meaning that's the port that takes you to the root bridge, or that's the port with the lowest possible cost. And this port, just like the designated forwarding ports on the switch, is open to send and receive traffic. But then, in this loop, for example, we have to block one of the ports. The way we determine which port to block on this link is by comparing the priority on both switches. Whoever switch has a lower priority, or in case if the priority is a tie, we compare the MAC addresses. Whoever switch has a lower priority or lower MAC address is set to have a designated port, and the other has set to have a blocking port. Well, in our case, it's obviously the switch A has a lower priority, or at least a lower MAC address than switch B, because he is the root bridge. And switch B is not the root bridge. He gets to have the designated port, and switch B has to have the blocking port. But just like we said before, the way the spanning tree actually monitors the topology and determines when there is a network change, or if one of the links fails, so you had to open another one, is by exchanging small packets called Bridge Protocol Data Units, or BPDUs. Those packets, by default, they exchange in every 2 seconds, even though you can actually configure that value to be in less than a second. But let's take a look at what does one packet have inside. These are the typical fields of the BPDU. Well, the first will set by the bridge ID. The bridge ID is basically the sum of the bridge priority and the bridge MAC address, which we already said that every switch has. So that means that every switch has a unique bridge ID, because remember that even though the priority is the same, there are no two switches that have the same MAC address, so they will always have two different bridges ID. So every switch has a bridge ID. Then inside on the BPDU, we have the root ID, which is basically the bridge ID for the root bridge, and then another field, which is the cost that takes you, or that takes your bridge to go to the root bridge. Then the hello timer, which is after how many seconds or in what interval the BPDUs are sent, and a maximum age timer, which is after how many seconds, if I do not receive a BPDU from my neighboring switch, I'll consider changing the network, and I'll start to reconverge on that network. But okay, let's see now an example of configuring spanning tree on a better way. Now imagine this is some sort of a topology, and all those, imagine that for every single switch this is their priority. In our case we're going to use the default priority, so on every single switch the priority is the same. So we cannot determine which one gets to be the root bridge, so we have to choose the root bridge based on the MAC address. If this is the MAC addresses for all the switches, then by looking at them we determine that switch A has the lowest MAC address out of all the other switches. That means that he gets to be the root bridge. Because we said that all the ports on the root bridge are designated forwarding, meaning they're open to receiving traffic, that means that those two ports on the root bridge will be designated forwarding. Then the next step of making a loop-free topology is by determining the root ports on every non-root bridge. Well, the root port was based on the cost, and it is said that all those links here have exactly the same bandwidth, which is 100 megs. And if you remember, the cost for 100 meg was 19, so that's why we're going to put 19 here. Now switch B has two possible ways to go to the root bridge. One is through F01, which is going to cost him 19, and the other one is through F02, which is going to cost him 19 plus 19, that's 38. Obviously switch B will choose F01 to be its root port, meaning the port that takes him to the root bridge. In a similar manner, switch C will determine that F03 is his port that takes him to the root bridge, or which is the port with the lowest cost. That is why he's putting R on it. And both R's and the D's, meaning the designated port and the root ports, they can send and receive traffic. And then for switch D, since this is the only path to the root bridge, he has no other choice but just to R and make this port a root port. And because this is switch D's root port, switch C cannot block that port, so he has to make that port a designated forwarding, meaning open to send and receive traffic, since this port is switch D's only way to get to the root bridge. Now we have to determine everything else. Well, for the hosts, eventually the switches will determine that there is no way they can get loops from there. That is why they have to open the ports and making them designated forwarding, meaning the ports connected to the end host devices. And there's a still loop existing, and because of that, switch B and switch A has to determine which of their ports has to be blocking. The way they determine which of those ports get to be blocking is by comparing their priorities and their MAC addresses. It is said that the switch with the lower MAC address or the lower priority gets the designated port, and the other one gets the blocking port. Well, since their priority is the same, we would look at the MAC addresses, and I see that the switch B's MAC address is lower than the switch C's MAC address. That is why switch B will put a designated forwarding on his port, and switch C will put blocking port in his end. Now that the switches have made up their loop-free topologies, they will still continue using BPDUs and sending BPDUs every 2 seconds in order to maintain or monitor that topology. But imagine that if the open link fails for some times, maybe cable got bad or anything like that, the root bridge or any other bridge for that matter won't be able to receive BPDUs. So now in this case, switch B won't be able to receive BPDUs. Well, if switch B does not receive BPDUs from the root bridge for 20 seconds, which is the max age timer in the BPDUs, he'll consider that there is a change in the network. In that way, the switch B will have to find a new root bridge or a new path that takes him to the root bridge. Well, out of all its options, he has only one other option to go to the root bridge, and that was the F02. But in order to ensure that there will be a loop-free topology, the F02 doesn't go to a root port directly, but it goes to another state called a listening state. In the listening state, the two switches will exchange BPDUs, and then they're trying to determine if there may be a new entire root bridge, or there may be some new root ports, or some other new paths, and so forth and so forth and so forth. So they're trying to determine their loop-free topology. Usually the duration of the listening state is 50 seconds. then the switch will go, and then the switch B will determine that that's its new root port. But again, it will not go to the forwarding yet. After the listening state, the port will go into something we know as a learning state. In the learning state, the switch will read the source MAC addresses of all the traffic that he receives, all the packets that he receives, and he'll try to populate his MAC address table as much as possible through that new port. But after it reads the MAC address of those packets, he'll actually discard them. He'll not forward them to their destination, but he'll just rather read the MAC address, write it in his MAC address table or his content address memory table, and then he'll discard the packet. The learning state goes also for another 50 seconds. And after the learning state, that port, since it was determined to be a root port in the first place, gets to be the new root port. So the actual host A's and servers can exchange the information. And again, the switch A and switch B will actually continue to monitor that port, and if that port fails for some reason, or the first port got open, then they will actually do another series of changes. Another state that exists in the spanning tree protocol is what we know as blocking port. We already seen that, which is blocks all other traffics, and he does not send any BPDUs. The switch does not send any BPDUs through the blocking port, but what he can do, at least from that port, is receive BPDUs from the other side. But it actually takes 50 seconds for spanning tree to reconverge. That is 20 seconds for the spanning tree to determine that there's a change in the network, then 15 seconds to go into listening state, another 15 seconds to go into learning state, and so it takes about 50 seconds for spanning tree to make up a new loop for topology and make sure that your communication goes. Well, that is good, but spanning tree behaves much the same way even when you just connect some different hosts to the switch. So even though they're n-host devices and there is no chance of loop, the spanning tree doesn't know that, so on those ports he has to go through listening state, he has to go through learning state, and then only then he'll be able to open those ports for the for the hosts. Well, that is long for a lot of time for some impatient user, so there had to be some other way of speeding up the process of spanning tree when we're talking about n-host devices. And the way to do this thing is by using the command spanning tree port fast. Port fast is a neat feature of spanning tree that allows a given port to be into designated state all the time, regardless of whether there's a network change or not on this port. Of course, you should have to use this command with caution, or this feature with caution, because if you configure this port or if you configure this feature appropriately, you might actually cause a loop, because this port, this command again, forces this port on the port that you configure that command to be a designated forwarding port, no matter whether there's a network change or not. So in our case, if you want to configure port fast on host A and we don't want to make him wait, we would have to go into global configuration mode and go for the interface that is connected to a host A. In our case, the interface is F03. That is why I'm typing the command interface F0/3, which will take me to the config-if sub mode, which was the sub interface. And then I'm just going to type the command spanning-3 port fast. After you type this command, the switch will shout out, or it will display a warning saying that you should be very careful with this feature again, and you should only configure this feature on access ports. And since you already know the access ports, those ports that are usually connected to n-host devices, that is what he actually means. Okay, but now let's get back together to the previous lecture that we did about VLANs and trunks. Now imagine that those two hosts right here are in VLAN 20, as well as those two hosts are in VLAN 20. Then this host and those two hosts are in VLAN 10. Now, if we want to make the trunks between the switches, let's make this trunk between the switch A and switch B to be able to carry traffic for only VLAN 10. The trunk between switch B and switch C to be able to carry traffic only for VLAN 20, and then the switch C and the switch A, the trunk between them, to be able to carry traffic for those two VLANs. So everything is good, and now if one of the hosts on one of VLANs, let's say VLAN 20, wants to talk to another host in VLAN 20, you have no problem passing that trunk, right? You won't be able to go through switch B, switch A, and then switch C because this trunk doesn't allow traffic for VLAN 20. Everything is good. But now let's put spanning tree into the picture right now. And if we make switch A to be the root bridge, that means that his port has to be designated forwarding. Then switch B and switch C has to choose their own root port. Now if switch B determines that to be his best path, meaning that to be his root port, and switch C determines that that has to be his root port as well, everything is good. But now one of the ports on switch B or either switch C has to be blocked in order to eliminate the loop that we have here. Well, if switch B has a lower priority than switch C, that means that he has to get the designated port, and switch C has to get the blocking port. Now spanning tree has eliminated the loops, we still have backup, everything is good. But now there is a problem that spanning tree created. Well, the problem is that now if the host on the VLAN 20 wants to talk to the other host on VLAN 20, he won't be able to because spanning tree is blocking any kinds of traffic that's passing through that port. Well, the solution to that problem, meaning the solution to the problem of spanning tree running as well as the VLANs and trunks running, is something called per VLAN spanning tree protocol. The per VLAN spanning tree protocol is that the per VLAN spanning tree protocol runs a separate spanning tree instance for every single VLAN that is running right now on the switches. So that means that now, in our case, there are 3 different spanning tree instances running at the same time on this topology. One for VLAN 10, one for VLAN 20, and then one for the VLAN 1, which was the default if we studied the last week. And because we said that by changing the route, the bridge's priority, we can alter who gets to be the root bridge. Now with per VLAN spanning tree protocol, we can actually alter who gets to be the root bridge for the different VLANs. That means that now I can erase the previous spanning tree protocol, which was for the entire physical topology, and I can make switch A to be the root bridge for only VLAN 10, and then I can make switch B to be the root bridge but for only VLAN 20. And then it says that those two are entirely different separate spanning tree instances. If for switch A, since he is the root bridge for VLAN 10, he gets his ports designated forwarding, but only for VLAN 10, only for traffic for VLAN 10. Then switch B will have to choose its root port, and then switch C has to choose its root port, and then switch B and switch D will choose their designated and blocking port, which was just like the case in before. But this spanning tree configuration, remind you again, is just for VLAN 10, it's just for traffic for VLAN 10. Now for VLAN 20 the things look differently. Since switch B is the root bridge for VLAN 20, he gets his port to be designated forwarding, then switch A and switch C has to choose their own root ports, and then the trunk between switch A and switch C, one of them has to be blocking, one of them has to be designated, and let's say switch A has a lower priority or lower MAC address than switch C, that's why he gets designated port, and switch C has blocking port. Now that means that the loop is broken right here on switch C for VLAN 10, and it is broken right here for switch C as well on VLAN 20. So if the traffic goes from the one host on VLAN 20, you have no problems now going to the other host on VLAN 20, because the trunk that carries traffic for only VLAN 20, as you can see, is open, but it's blocked that is carrying for traffic for VLAN 10. And we have no problem with that, since in the first place this trunk was not allowing traffic for VLAN 10 to pass. Okay, but now let's see how we can configure per VLAN spanning tree protocols and what commands can we use to alter the bridge's priority for different VLANs so we can make our network more flexible, or our topology more flexible. Well, the first command that we can do is in global configuration mode on the switch typing spanning tree mode PVST, which will tell the switch to start running per VLAN spanning tree protocol. But needless to remind you that per VLAN spanning tree protocol was created by Cisco, and it is the default spanning tree mode that is running on the switches, so you don't have to type this command if you want to run this option. However, if you change the spanning tree mode to some other mode, And if you want to go back to per VLAN spanning tree, this is how you can do it. Then if we want to make our switch to be the root bridge for a given VLAN, this is the command that you have to type. You will have to type spanning -tree VLAN and then the VLAN that you want to configure spanning tree for, and then you type root primary or secondary. If you type root primary, spanning tree will ensure that this switch will be the root bridge for this VLAN, and if you type secondary, spanning tree will ensure that this bridge is the secondary root bridge, means that if the primary fails, or the seconding command for that VLAN that you have typed. But those two commands still doesn't give us a lot of flexibility, so you, instead of the spanning tree VLAN root primary and secondary, you can use the command spanning -tree VLAN and the VLAN that you want to configure spanning tree for, and you type priority and then the priority value. I should remind you, or I should warn you, that the priorities values, they go of increases of only 4096. So you cannot have a priority of 3, 4, 2000, 5000. All you can have is you can have priorities of 0, 4096, 8192, and so forth and so forth and so forth. All those commands are written in, or I typed in global configuration mode of the switch, so you should not type it in anywhere else. But now let's see how we can use those commands to configure this topology to look like the one we did before, meaning the switch A to be the root bridge for VLAN 10 and the switch B to be the root bridge for VLAN 20. Well, all we have to do is, since per VLAN spanning tree protocol is running by default, all we have to do then on switch A, in global configuration mode, we would have to type spanning -tree VLAN root primary, which will ensure that the switch A is the root bridge for VLAN 10, and it will result the spanning tree topology to look something like this, but for VLAN 10 only. And we can type spanning -tree VLAN 20 root secondary. That means that the switch A will be the backup root bridge for VLAN 20. The similar picture we can do for switch B. In global configuration mode, we can type spanning -tree VLAN root primary, which will ensure that the switch B is the primary root bridge for VLAN 20, and will make the spanning tree instance to look something like this. We already said that. And so now we have two spanning tree instances running on the same topology for the two VLANs, and switch A is the root bridge for VLAN 10, but switch B is the root bridge for VLAN 20. And if we want to make switch B to be the backup for VLAN 10, well, that's easy too. All we have to do is, in global configuration mode, type spanning -tree root secondary. But even with the VLANs, spanning tree still takes 50 seconds to reconvert. 20 seconds for the max state timer, then 15 seconds in listening, and then another 15 seconds in the learning state, which is still a long time. Well, luckily for us, there's a rapid spanning tree protocol. A rapid spanning tree protocol does not have a blocking port like the regular spanning tree protocol has. What does it has? It has an alternate port. The alternate port, under normal conditions, act like a real blocking port, meaning it blocks all the ports with no problems whatsoever. However, the alternate port is basically meaning that it is an alternate port for the root port, meaning this is an alternate way to go to the root bridge. So if, let's say, this port between switch B and switch A fails, meaning the root port for switch B fails, when switch B determines that this is going to be his new root port, when he sends the BPDU to switch C, switch B will not take any time to try to determine whether or not by opening this port he will result into a loop, but he will rather make this port going to designated forwarding immediately as soon as he received the BPDU indicating that now this port is switch B's root port. Why did he do that? Well, because in order for switch B, or the only case when switch B will change his root port to this root port is if the topology failed on some other place. And if the topology failed on another place, that means that the loop is broken in one more place. So if me opening this port, I will not result any loops because it's being broken into one more place. The way to configure rapid spanning tree protocol is all you have to do is type the command in global configuration mode spanning tree mode rapid PVST. And actually, you're not configuring spanning tree or rapid spanning tree only, you're configuring rapid per VLAN spanning tree. That means that this is a rapid spanning tree protocol running for every single VLAN. So it's like per VLAN spanning tree protocol and rapid spanning tree protocol running on the same time. One command that we can use to verify the spanning tree configuration is in privilege mode. We can type the command show spanning tree VLAN and the VLAN number. Another command we can use to verify our configuration is basically typing the show running config command. But now let's see what the show spanning tree VLAN command will do. This is a typical output of the show spanning tree VLAN command. And if we type it on the switch C for VLAN 10, this is what it's going to look like. Now, the first thing we will say is that the spanning tree enabled protocol is STP or rapid spanning tree protocol. But since we're talking about VLAN 10, that means that the actual protocol that is running is rapid per VLAN spanning tree protocol. Then the next thing it will say that the priority for the root bridge is 24,586, and this is the root bridge MAC address. And the root port, my root bridge, I can reach the root bridge through port F011, and then I'm sending BPDUs every 2 seconds, and if I do not receive BPDU in 20 seconds, I think that something is wrong. Then this is my own priority, which is the 32,778, and this is the MAC address for the bridge or my bridge. And then again, I'm sending packets the same time, and if I do not receive BPDUs in 20 seconds, I think I think that there is something wrong. And then if you see the ports, it says that F011 is my root port and his cost is 19, and the cost is 19 because this is a fast Ethernet and it has bandwidth of 100 megabytes. And then F012 is an alternate blocking port, but we said that the alternate blocking port is nothing more but an alternate port for the root bridge for some other bridges. And that is why if switch B, when we did the first connection, if switch A loses its root port, this can go into designated forwarding immediately. And that's it. That's pretty much all you need to know about spanning tree to be able to configure it and troubleshoot it in your real life topology. You have to choose either per VLAN spanning tree protocol or rapid spanning tree protocol, and then configure the different root bridges for the different VLANs in order to make your network more flexible, in order to allow different traffic to pass through different sections of your network, thus performing load balancing. But let's just to recapture what we did in this lecture is first we introduced some problems in the redundant topologies like broadcast storms, multiple frame copies, or MAC address table instabilities. And then we introduced ourselves a spanning tree, saying that this was the spanning tree protocol, which allows us to dynamically block one of the ports of redundant topology and then monitors the open one in case if this one fails, I will always unblock the other one. Then we talked about how actually spanning tree reconverges, going through different states of listening, learning, forwarding, blocking, and so forth and so forth. And then we said that because in our daily lives almost everyone uses VLANs and trunks, we had to invent a new type of spanning tree protocol, which was the per VLAN spanning tree protocol. And then we had the rapid per VLAN spanning tree protocol, which instead of a blocking port had the alternate port, which allows us faster convergence of the entire topology. And then we learned how to configure and verify the rapid spanning tree protocol. Thank you very much, and I hope I'll see you soon.